Hello, let us come back to the problem that we were discussing. We want to calculate the bands of a solid when there are n number of atoms in a solid in a regular periodic arrangement, and we want to know we want to basically solve the Schrodinger equation for an electron moving under the potential of all these atoms. Now, to do that we need to understand a few things before we embark on that solution, and one of the celebrated ideas and theorem and a theorem that is important to know is the so called Bloch's theorem, and Felix Bloch did it, worked it out, and then the theorem basically states about the possible solutions to the Schrodinger equation when a particle moves in a periodic potential. So, let me just first tell you what a periodic potential is, which probably many of you know already, but let me just digress a bit. Now, a periodic potential is a potential which repeats, which is periodic in space, and the left hand picture, for example, gives an illustration of such a periodic potential in a one dimensional lattice. For example, if I have this kind of a lattice atoms here, then the atoms of course attract the electrons. Their potential will have a structure which is like this. For the as the electron passes, it will see a potential which is like this, right. So, it will be a potential like this. Deep potential. Remember our very zeroth level discussion that we replaced these potentials by a infinitely deep potential in a box, and that is exactly what we are doing here, but more realistic. Just these boxes are replaced by the Coulomb interaction that is there in a solid. So, this was the kind of thing that picture we drew, whereas now we have fixed atoms. We are not bringing atoms together, they are already there, they have a fixed distance, and in this case we will like to see what is the solution of the Schrodinger equation for an electron which is moving in this potential. Okay. So, that is the problem. So, the problem is very well defined. It is a problem of an electron moving in a potential of a periodic arrangement of atoms. These atoms are all having their attractive interaction on the electron, and this attraction has a shape which is what I have just drawn. On the left hand side, the better drawing has been done. The solid black line is the potential. It has it is deep down at the location of the atom. So, this is the if you can look at this, then if you see this, these are the locations of the dots are the locations of the atoms, and the potential is deeply positive E square by r, and as r goes to 0 it goes negative minus E square by r, because it is an attractive interaction. So, it goes deeply negative at the location of the potential. As r goes to 0, it will just diverge in the negative direction. But between the atoms, of course, it immediately very fast becomes 0, and then the interatomic space, there is a region where the interaction between the nucleus and the electron, between the nucleus it has just passed, and the nucleus it is coming to this is both of them are they almost cancel each other, and then that means the electron is more or less free in this region. So, the problem then in mathematical terms is what is written here, that you have a potential which has this structure. The potential u is such that any r to the potential at any point r, if you add capital R to it, it will just repeat itself. That is exactly the nature of this picture. Picture shows that you take the potential at any point r, and add this interatomic spacing capital R, then you will see that the potential is the same at R plus R. So, that is exactly what, and you can go on doing it ad infinitum. So, it is this R can be 1 lattice spacing, 2 lattice spacing, 3 lattice spacing, n number of lattice spacing, it will be the same. Actually this guarantees that, right, u r plus capital R equal to u r, so then you add another capital R, then on the right hand side you will get another u r plus R, which is again u r. So, u r, this is the u r plus 2 r, for example 2 into R is u r plus R plus R, which is u of R plus R, which is again u r. So, you can go on doing this. I mean, this is there is so that means n, you can add as many capital R's as you want, and where you will get the potential to be the same. And capital R here is it's basically it's called a Bravais lattice vector, which I will come to, but in this one dimensional picture it is basically the interatomic distance. So, the purpose of this whole exercise is to solve the Schrodinger equation under such a potential, which is given which is written down here, H psi equal to, this is the time independent Schrodinger equation, minus H cross square by twice m del square plus u of r of psi is equal to E psi. So, that is the equation that we are after. So, this is called the independent, this is of course independent electrons, because remember we have only one, we are considering only one electron or a large, I mean it does not matter if you have n number of electrons which are not interacting with each other, we will still solve the one electron problem and find out the states, the solutions, and put n number of electrons in, starting from the lowest solution, lowest eigen energy, eigen state. Okay. So, this is the problem at hand, this is what we intend to solve. Now, this is where the Bloch's theorem come in extremely handy, because what Bloch theorem shows is that the solution the states, let me just state it, the eigenstate psi of the one electron Hamiltonian can be chosen to have the form of plane wave e to the power I k dot small r times a function u of r having the periodicity of the Bravais lattice. Again I will discuss Bravais lattice little bit, probably all of you know it, but I will come back to what Bravais lattice. For us, for this one dimensional picture that I showed, it is again the interlattice spacing. So, this is the so this psi k of r is e to the power I is like a plane wave, except that it is modulated by a function u k of r, where u k of r is such that it is equal to u k r plus r. So, that is the interesting part to it. So, that is called the Bloch's theorem. So, Felix Bloch first wrote it down. In different contexts there is a theorem called Floquet theorem, which is similar to it, but let us not discuss that. This is the theorem that is extremely handy, and it allows us to choose certain kind of wave functions, and it also tells us what should be the property of the wave function that we are looking for the solution. And this is an exact theorem. If the potential is periodic, then your solution must have this form. It is a plane wave times a function u of r, which is what I have written down, which may depend on k, which I may or may not choose k here. Ideally, it could also depend on k, but hardly matters. We will this for the time being let me not put k here, but this is the general solution. This is the solution that Felix Bloch predicted. This is the nature of the solution. So, this is the property of the solution. It is not that we are giving you a solution, we are telling you what the property of the solution should be. Solutions of course have to be obtained from the equation, but then we can check whether the solution is follows this theorem. Okay. So, alternately you can also write psi k of r is equal to, so let us just move this wave function by one lattice vector, then let us see what happens. So, e to the power I k r plus capital R into u of r. Now, r plus r is the same as r, so I can write as u of r. Okay. Now, it is, you can see that it is e to the power I k dot capital R times e to the power I k r into u of r, which is psi of r. So, this is e to the power I k dot r into psi k of r. So, that is a beautiful result, because it just tells me that if I move this position of the function by to a nearest neighbor lattice site from any site, then I will only have to do is to put a factor e to the power I k dot r, just a phase factor, which is I k dot r, where this k will have to be determined, that comes from the solution. So, that we will do later on, but at the moment this just tells me that there is just a phase factor that has to be added to the wave function to go to the next nearest neighbor. To the further one and further one and further one, we can just add these phase factors and move on and on and on. So, if we know the solution at a particular r, then we know the solution everywhere. Okay, we know just adding a phase factor will give me the solution. So, that is a very powerful theorem, because you are dealing with an infinitely large lattice, and it tells me that if you have the wave function at a particular r, then you know everywhere what the wave function should be. So, very important and useful theorem to work with. Now, to prove Bloch's theorem, let me just go back and discuss a bit about the lattice. We have been talking about lattice, Bravais lattice and so on. So, let me just show you an example of Bravais lattice. So, take for example, so this is an interesting example, it is a counter example. I will just come to what a Bravais lattice is. See, Bravais lattice, the definition is very simple. The definition of a Bravais lattice is basically, I mean, if you have a lattice, for example, if you have a arrangement of atoms, for example, this is an arrangement of atom, this is another arrangement of atom, all these arrangements can be, you can see that in all these arrangements, from any point, take any point, if you look at the lattice from that point, then the lattice looks the same. So, it is not only the arrangement, the orientation will also look the same. So, that is what is a Bravais lattice. So, in 2 dimension I have drawn now these 2 lattices, both of them are Bravais lattice, because from any point you look around you, around this point, the arrangement as well as the orientation look the same. So, that is called a Bravais lattice. There is a formal way of writing it also, but this so let me just write down the formal way. So, as I said, a Bravais lattice is an infinite array of discrete points with an arrangement and orientation that appears exactly the same from whichever of these points the array is viewed. Okay. So, let me repeat, it is an infinite array of discrete points with an arrangement and orientation that appears exactly the same from whichever of these points one chooses to look around. So, that is the way one gives a definition, where it is not a mathematical way of looking at it, but it is a perfectly good definition of a Bravais lattice. Such lattices, such arrangements are called Bravais lattices. Mathematically you can for example, in 3 dimension you can choose a vector. So, say for example, r equal to n1 a1 plus n2 a2 plus n3 a3, where a1 a2 a3 are 3 vectors, not all of them are on the same plane. This is in 3D, for example, we are doing 3D here. So, so they are in 2 dimension, of course, they have to be in the same plane, you do not need the third vector, but in 3D you need these 3 vectors to define it, and these are a1, a2 and a3 are just vectors which any 3 vectors, not all are in the same plane, and this n1, n2 and n3 are just integers. By integer one means 0, plus integer, minus negative integer, all. So, this is basically the definition of a Bravais. So, this R, capital R, spans a or generates a Bravais lattice. So, that is the formal, another way of looking at it. It is a mathematical way of writing it down. These vectors a1, a2 and a3 are called the primitive lattice vectors, and they generate this the lattice, the Bravais lattice by generating these points R. Every point R, by from n1, n2, n3 being integers, you can just generate as many R's as you want, and that generates the Bravais lattice. So, as I gave an example, for example, this is this in this case, for example, I can choose 2 vectors a1 and a2, and this is my origin. So, take the point, for example, this point P and this point Q. I can write P as 2a1 plus a2, right. The vector P connecting origin to P can be written as 2a1 plus a2. So, this n1 here is 2, n2 here is 1 and n3 equal to 0. Similarly, if I want to get to this point Q, then I will go minus Q will be minus a1. So, I come here and then go one step a2. So, that is my, so minus 1 and 1 are the n1 and n2 here. So, that is exactly what one is saying, that this definition of these R's that you can generate are making giving you the lattice that you want. That lattice is called the Bravais lattice. Now, here is on the left side I have chosen I have shown chosen to show actually a lattice which is not a Bravais lattice. Now, let us look at this left hand side picture, this one for example. Now, if you look at this lattice, look at the point P and then look at the point R. From P, if you look around, the arrangement looks to be the same, but the orientation is not. Just look at carefully from the point P, which is this point. this point P. Okay, this so this point has a point on the left side, right, on here. If you look up left, there is a point here, nearest neighbor, whereas this R does not have a point here. So that is an interesting example that this lattice is not a Bravais lattice. In fact, you can actually check for yourself. If you take this point P and R, if you take point P, the neighborhood that you see will be seen exactly from the point R if you just rotate this page 180 degree. Just rotate 180 degree, full circle, half circle, then you will see this. So you rotate it by 180 degree, this picture, then you will see that Q R will now look like P. The neighborhood of R is exactly like that of P. So this is an interesting exercise. You can take a printout of this or just draw it on a piece of paper and rotate it, and see that only if you rotate 180 degree can your P and R look the same. By looking the same, I means view the lattice from that point and your view should be the same. So so for example, if you look at Q is very similar to P, exactly similar to P actually. The view from Q and the view from P are the same, and this lattice is actually a honeycomb lattice, and this is not a Bravais lattice, although this is a lattice. This is a regular, I mean by lattice I mean a regular arrangement of points, but its orientation has this problem that it is not the same viewed from every side. So that is not a Bravais lattice. Now the interesting thing you can also check is that if you put a point at the middle of this lattice, another point in the every hexagon you put one middle, at the middle another point, you will end up getting a triangular lattice, and that is a Bravais lattice again. Then you will find that all points represent same view whichever way you look at. So this is a celebrated example now, because for the last 10 or 15 years graphene is the hot topic. Everybody discusses graphene. So many new properties have come up for graphene, and you can look up in the literature and see that graphene has this kind of a lattice. So the question then is, what does one do with that kind of lattice? Can't one do a band structure for this kind of a lattice? The answer is of course yes. The way to do it is to choose a unit cell which will, for example, when after you make the unit cell choice, every unit cell should become equivalent. So that is a choice has been shown here. For example, each of these parallelograms here on the right hand side, each of these parallelograms that you have has 2 atoms of this lattice. Assuming that the atoms are all the same, both atoms are same, or even if they are different you could choose, but these in graphene for example both are carbon atoms. So then what you do is that you choose your unit cell to be this parallelogram for example, and any point inside the parallelogram can be chosen as a new lattice point, and the equivalent point in next parallelogram has to be chosen as the lattice point, and that way you can construct a new lattice, and that lattice is a Bravais lattice. So this is called the choice of unit cell, and a unit cell with a basis. So this, for example, in this case when I had this choice on the right hand side, for example here this I could choose a unit cell with only one atom, because all atoms are equivalent. Viewed from if you view the lattice from every atom, it is equivalent, but here it is not. So I have to choose a unit cell in such a way that the view again becomes equivalent, and then of course this is a Bravais lattice of the new lattice with a basis is again a Bravais lattice on which you can now do a band structure. That is more complicated, but it is doable and it is routinely done. So this is for example the celebrated example of graphene. So, what one shows here is A and B are the A is the real lattice and B is the reciprocal lattice. You have all done reciprocal lattice. So, the reciprocal lattice is constructed here. A reciprocal lattice of this kind of a lattice is a hexagon, and so it's just a rotated hexagon. You can see that the line here is at the top, here the point is at the top, but it is still a hexagon. And the other thing is that you can choose these vectors a1 and a2. This choice is not unique, remember. I could, for example, on the right hand side, this picture I am showing, I could as well choose any two other vectors. For example, I could choose this and this as my new unit vector, new primitive lattice vectors. So, that will perfectly describe the lattice. Again, every point can be described by that lattice choice, this choice of unit cells, choice of primitive lattice vectors. Here a convenient choice is for example a1 and a2. So, this a1 and a2 represent the a1 a2 that I have written here, and the lattice is spanned by this these two vectors, and the unit cell that you have to choose is this yellow one, which is what I have done in the previous slide, for example. And the Brillouin zone is this right hand side B. Gamma point is the central point, k equal to 0 0 0. This is called M point, this is k point, and this is k prime point. These 2 points are inequivalent, and so, and then the reciprocal lattice vectors are B1 and B2. So, this is how graphene is worked out, and at some point if we have time, I will just tell you what the band structure of graphene is, because that is very important in today's context.